You can update the character at any position in the string, as many times as you're asked. And after each update, you need to report the length of the longest run of identical characters sitting next to each other anywhere in the string. You've got a string, and every edit changes one character. After each edit, tell me the longest run of the same character, instantly. Hey, I'm Kai, and this is Fun with Learning Technology. This one looks scary because it says hard, but honestly, it's one clean idea done right. Let's break it down. You get a string S, a list of characters to place, and a list of indices to place them at. After every single update, you return the length of the longest stretch of one repeated character. Sounds simple until you realize you might get 100,000 updates on a string that long too. This exact shape shows up anywhere something keeps changing, and you still need a live answer. Collaborative editors, streaming analytics, even compression tools. And here's the thing, everyone assumes this needs a heap or some fancy data science trick. It doesn't. By the end of this video, you'll spot this pattern in seconds. Take the string B, A, B, A, C, C. First query says put a B at index 1. Now the string reads B, 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 A, C, C, C. 3 B's in a row, so the answer is 3. 2 more queries follow, and each time we need a fresh answer, fast. We'll turn the string into a list so we can change one character at a time. The real engine is a segment tree, a tree where each node summarizes a chunk of the string. We use recursion to build it and to update it, and a small dictionary per node to hold its stats. Someone edits one character in a huge string. The naive fix rescans the entire string from the start. As the string grows, that rescan gets slower and slower. Given a string, find its longest run of one repeated character. In a B, B, C, 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 D, the answer is 4, from the run of C's. The real challenge, answer this again instantly after any single edit. Walk the string left to right with a running counter. Same character as before, bump the counter. Different character, reset the counter to 1 and keep the best seen so far. This is the whole naive scan. 1 pointer, 1 counter, 1 comparison per step. It's correct, and it's the foundation everything else builds on. But run it after every single edit and you're doing this whole walk again and again. The single pass itself isn't hard, you could write that in your sleep. The real difficulty is answering this question over and over after every edit, without walking the whole string each time. An edit at position I can only break or merge runs right around I. Everything far away from the edit stays exactly the same, so we only need to recheck a small local window, not the whole string. Split the string into a tree of segments. Each node remembers its longest run, plus its run touching the left edge and the right edge. Merging two children combines those edge runs to get the parent's answer. Change one character. Update its leaf node. Walk back up to the root, recomputing each ancestor from its two children. Only log n nodes get touched, no matter how big the string is. And that just dropped us from big O of n down to big O of log n per edit. Merge takes two child summaries and builds the parents. If the left child's rightmost character matches the right child's leftmost character, their edge runs can combine. That's the +0 or plus the other side's run you see here. Update just calls merge on the way back up. Here's the whole thing in one place. Build the tree once, then for every query update one leaf, walk up and read the root's max run. Clean. That left edge run calculation looks tricky, so let's use real numbers. Say the left child is 3 characters, all the same letter, so its left run is 3, the full length. Since it fills the whole segment, it might keep growing into the right child. But if the left child were BBA, its left run is only 2, less than its length of 3, so it stops right there no matter what's on the right. Start with BABACC, put B at index 1, string becomes BBBBACCC, longest run is 3. Put C at index 3, BBBCCCC, 3 B's or 3 C's, still 3. Put B at index 3, BBBBCC, now 4 B's in a row. Quick one for you. The string is AAAA, and you place a Z at index 2. Pause the video and work out what the longest run comes back as. Then drop your exact answer in the comments before I show you next. The answer is 2. A, then Z breaks it, then A again, and 2 is the longest. The real mistake people make is only tracking each half's best run and forgetting that a run can straddle the boundary between two children. That's exactly why every node also stores its left edge and right edge run. You could instead keep a sorted set of where each run starts and ends, and merge neighboring runs by hand on every edit. It avoids building a tree, but tracking the current maximum needs a heap with lazy deletion, since old run lengths go stale. Honestly, that's more moving parts than the segment tree, not fewer. Building the tree once costs big O of n. Every query after that is big O of log n, since we only touch one path from leaf to root. With k queries, total time is big O of n plus k log n, and space is big O of n for the tree itself. A string of length 1 still builds a valid single node tree. Placing the same character that's already there just rebuilds that leaf with no harm done. And edits at index 0 or the very last index work the same way, since the update walk just goes all the way to that side of the tree. Remember that empty Rescan Trap from the start? Now you see why it doesn't scale. The key observation, and edit only disturbs, runs right around it. So we built a segment tree where each node stores its max run plus its left edge and right edge runs, and merges combine across boundaries. That gets every query down to big O of log n. The portable lesson: whenever an update only affects a small local region, look for a tree that summarizes chunks and recombines on the way up, instead of tree that summarizes chunks and recombines on the way up. Survive one more click, subscribe. If something feels off or missing, or you want to see something new, tell me in the comments. Quick one. If we rescan the whole string after every single update, what's our total time complexity across Q queries? Pause it and guess. Think about what rescanning costs you every single time. It's O(n) times QM. Every update forces another full pass, and that's exactly the Rescan Trap that pushes us toward a segment tree. Second one. When we merge two child ranges in the segment tree, what 3 pieces of info does each node need to store? Give it a guess. Think about what happens right at the seam between two ranges. Each node keeps a prefix run, a suffix run, and the best run inside it. The prefix and suffix are what let a merge catch a run crossing the seam.